In our last section, we saw that we could find the cell potential for a cell by looking at our reduction potential chart, finding our two half reactions, flipping our bottom half reaction to make it an oxidation equation, changing the sign on its reduction potential, and then adding those two together. This equation right here is a different way of saying that same exact thing. You take the reduction process, let's take the E of that reduction process and subtract the E of that oxidation process, and you get the E cell, you get the EMF of the cell. If you get a positive value for E, this indicates a spontaneous process or a negative delta G, and this is going to be true for voltaic or galvanic cells. If you get a negative value for E, then you have a non-spontaneous process, which is positive G, and these are found in electrolytic cells, which we have not gone over yet. We also saw that the thing that makes a cell work, its driving force, is the potential difference, or the EMF, or the voltage of the cell, the potential difference between the two half cells. Right here we have an equation that relates potential difference with work, not an important equation to know. Here's another one that's not that important to know, but we have a constant here that we really need to know, a Faraday. A Faraday is the charge on a mole of electrons, and it is equal to 96,485 coulombs per mole of electrons. Coulomb is the SI unit for charge. This constant is one that we're going to use a lot. You'll often see it written out as 96,500 coulombs per mole of electrons. And we all know just from common sense that you will never, ever, ever get 100% efficiency in any kind of work, electrical, mechanical, or whatever, because you will always, always, always lose some sort of energy in the form of heat. Heat is generated. Now we move down here, we're going to get to our first important equation right here, the relationship between delta G and E. Delta G, free energy, is equal to negative N times F times E, or same thing except at standard states. G is your Gibbs free energy. N is the number of moles of electrons that are transferred during the redox reaction. And then F is that Faraday's constant, E is E cell. So let's take a look at an example problem. Here we're going to calculate our free energy change and our equilibrium constant. To calculate our free energy change, first we're going to have to find E cell. So we're going to take this reaction, we're going to split it up into two half reactions. So I'm going to look at my little chart, and I'm going to look for the two half reactions that match this reaction. And I find this for my reduction reaction. For my oxidation reaction, I find that silver reaction, but I have to flip it. When I flip it, I change the sign. I'm also going to have to multiply this reaction by 4 because I need my electrons to balance. I do not multiply my E by 4. Now I'm going to take these two E's, I'm going to add them together, and I've got the EMF of my cell. Now that I have this, I can go ahead and plug it into my equation to find free energy. My value for N in this equation is going to be 4 because I had 4 electrons that were transferred in this redox reaction. In the value for F, Faraday, that's in coulombs per moles of electron. A coulomb is the same thing as a joule per volt. And so when I got done with this equation, my unit was in joules per mole. I can change that to kilojoules if I want to, but I'm not going to because I'm going to need it in joules for the next part, finding the equilibrium constant. Okay, so I'm going to use this equation here, one we've used before, and I'm going to solve for K. And I get this really huge number, which agrees with everything else I've solved for. This really big number indicates that this should be really spontaneous, which I got a negative value for delta G, so that's good. And I got a positive value for E, also indicating a spontaneous reaction. So all of these things agree with one another. Now, for standard cells, all your concentrations on both compartments are 1 molar. But here's the deal. As soon as you turn this battery on, those concentrations start to change. Why do they change? Because your ions start to move. This is your little battery with your little half cells. Your ions are moving all around in here. And so the concentrations of your solution start to change. And since your concentrations are changing, your EMF immediately starts to change. So these values that we get here when we solve for EMF, these are initial values at standard state. And as soon as you turn your battery on, that value starts to drop. And we know that. We know that as soon as we start using a battery, the battery starts losing its power. And at some point, it's going to go dead. When the battery goes dead, that means that your cell has reached equilibrium. And your EMF, or your cell difference, your potential difference, is going to be 0. So if you change concentrations, your voltage is going to change too. Your cell potential is going to change too. There are two ways to deal with this. One way is qualitative, in which they say, all right, if you change the concentration of some part of your cell, what's going to happen to your potential? Now you can use Le Chatelier's principle to figure out what direction the reaction is going. For example, okay, here's my little cell. Let's say I add some of this, and it's going to shift the direction of my cell over to the right. If you shift to the right, you tend to increase your cell potential. If you shift to the left, it tends to decrease the cell potential. This has to do with the shifts in K, and we're going to look at that here next and see exactly what causes that. Now, quantitatively, you can figure this out by using a wonderful equation called the Nernst equation. Now, the Nernst equation is not one that they expect you to have memorized, but it is in the equation sheet and they expect you to use it. Now, it can be written several different ways, and since they change the equation sheet around every year, there's no way to know what way they're going to write this. So you take a look at the equation sheet that I gave you and see, what this is going to look like. It could look like this one here, could look like this. It could look like this. It just depends. But all of these mean the same thing. It's a way to calculate out the potential of a cell when it's not at standard state. And it says the potential of your cell is equal to your cell potential minus, and then they're going to have this or this or this, depending on what you're dealing with. N is always a number of moles of electrons in either ln Q or log Q, in which case Q is what it always is. It's just the reaction quotient, products over reactants. And again, as soon as you plug this battery in, its concentrations are going to start to change. And so its E cell is going to change. And then it's going to keep changing until it reaches equilibrium, at which point your cell is dead, your battery is dead, and E cell equals 0. So at equilibrium, your E cell is 0, Q is going to be equal to K, and you can manipulate the Nernst equation even one step further and end up with this over here. And so there are multiple ways you may see this equation. Again, don't memorize it, but be familiar with it and be ready for any that may come your way. So let's take a look at an example of using the Nernst equation. The key here is that they're giving you concentrations other than 1 molar. As soon as you see that, you know you have to use the Nernst equation. So to figure this out, the first thing we're going to have to do is figure out the value for E cell at standard state, which I'm pretty sure we have already done in a previous problem. When we did it, we got an E cell of equal to 0.79 volts. And we just used our standard reduction potential table to do this. Now I'm also going to have to find Q for this problem. To do this, I'm going to do products over reactants. Notice that there are no values listed for this solid or this liquid, and that's fine. They're not included in equilibrium anyway. When I plug these in, I need to make sure that I'm squaring, taking it to the 6th power, taking it to the 14th power. So now that we have our value for Q, we can go ahead and start plugging this into our Nernst equation. And I'm going to use this version. My value for N here, if I go back and look at my half reactions, is 6 electrons being transferred. So this is my setup. If I go through and solve, I end up about with 0.89 volts. And so when I changed the concentrations, the voltage actually went up a little bit. I can also change the concentrations and make it go down a little bit. And this kind of goes along with what we were saying up here if you you can cause it to shift one way or the other by increasing or decreasing concentrations, and as a result, because of that Q, it'll reduce the potential or increase the potential. I think we'll do this equation together, or this problem together in class, and we're going to skip on ahead to concentration cells. Since if you change concentration, you can change voltage, something interesting that can happen as a result is you can actually have cells that have the exact same components in them. They're made up of the exact same stuff, but if you give them different concentrations, they'll have different cell potentials, and so a potential difference will actually exist. So they have the same components but different concentrations, and a reaction starts to occur that tries to equalize out those ion concentrations, and so you get a voltage from this cell. This again is called a concentration cell. Concentration cells are very weak. They have really, really low voltages, and as a result, you're really not going to see these in use in things like batteries, but you do see them in small electronics and in biological systems. Nerve impulses work a lot using concentration cells. This last example problem, we're not going to go through. It's in your book if you would like to look it over, but the reason why I don't want to go through it is because it uses a combination of concentration and pressures, and so the Q starts to get really complex and complicated, and I found that it just causes a lot of frustration and difficulty when these problems really aren't that hard. So we're just not going to even mess with this example problem right here.